Stereophonic sound is a method where we reproduce a sound using multiple sources, so multiple speakers, to achieve an illusion of stereophonic sound, since we do have two ears and we use them to determine where the sound is coming from. Now, in the most common stereophonic signal, we have two speakers producing the sound, and this helps us to create an illusion of the sound coming from the left, from the right, as I've shown you already with reverb, further back, further forward. But we have more complex systems like 5.1, 7.1, quadraphonic, so we have systems with more than two speakers that help us even improve that illusion of where the sound is coming from the front, from the back, left, right. And when creating a soundstage, we can use that to our advantage. Now, in the most common stereophonic system where we have two speakers, to create an illusion of stereo, we can use various techniques. First and foremost, having the sound louder on the left or the right channel is going to make it seem like the sound is coming from that direction. Now, another principle that our brain uses to determine where the sound is coming from is by measuring the time delay between when one of the ears picks up the sound and then when the other ear picks up the sound. Now, that small difference of the sound reaching one of our ears first before the other one is what our brain decodes into positioning information. And of course, we can create that same illusion inside of our DAW just by delaying one channel, the left or the right channel, as I've shown you using delays. We can create an illusion of the sound being more stereo, so coming from one side or coming from the other side. Now, how do computers meter and measure if something is stereo or not? Well, the only thing they can do is actually check the correlation between the left and right channel. The correlation meaning how different are these left and right channels, how different is the phase of the signal at one point in time for the left and right channel. Now, we have something like that called the correlation meter, which you can see right here, down there, and it measures the phase difference between the left and right channels. When I produce a sound using a synthesizer that is purely mono, so it's one sine wave panned in the middle, it will create a mono sound, and it should be right here at hard right, at 1, position 1, meaning that the phase between left and right channels is identical. So I'm going to produce a sine wave. And as you can see, the signal is the same on left and right. Of course, that's just the amplitude. But if we saw that, we would know if the signal was stereo or mono. How stereo was it? So now right here, when it's hard pinned onto 1, it means that it's mono. The signal is mono. It's the same on left and right channels. If I produce that same signal on the left and right, I pan that to the left, I introduce one more oscillator that's hard pan to the right. So this one is producing the sound only on the right channel, this one only on the left. And I play that and I give them the same phase, I'm going to get the same result. See, it's mono, it's hard pin to the right, that's it. So it's mono, completely the same phase of both. Now, if I turn the phase of one of these upside down to 180, just like that, now they completely opposite phase. That would mean that this is the most stereo a signal can get, meaning that I'm expecting this correlation meter to show us -1, so the phase being completely opposite. Let's try that. Yeah, right there. Now, what we can do is introduce different levels of phase correlation like this by changing this phase. So you see, I can play with how stereo the signal is by just changing the phase of one of these two identical signals to show us how stereo it is. So what a computer goes by in determining if something is stereo or not is measuring the phase at every point in time of a certain signal on the left and right channels and seeing how different it is. The more different the phase is, the more stereo the signal is. And if this phase was completely opposite, like this, at 180, the signal is completely stereo. Now, if I put both of these signals in the middle, like this, we just reset both of these, we should now get no sound because these are completely identical signals with completely opposite phases. So no sound. I'm sending MIDI in, but no sound is coming out since they cancel each other out. Now there is other measuring tools that also shows us phase correlation along with the amplitude too. Like let's say this one, or let's say this one. So just a graph that shows us the phase. Let's see what that looks like when it's completely mono. Let me reset this. So you see completely mono right there. And anti-phase, what we are going to achieve right now, is going to be completely flat like that. Let's see that. All the way down there. Let's see what this change is going to introduce. All of these have the same thing. They just determine the difference between the phases of the left and right channels to show us graphically how stereo something is. Let's play with the phase and look at this one. Of course, now completely mono. And when we go more stereo, 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 just like that. Now, since this signal is completely identical on the left and right channels, see what we are getting? So completely out of phase, right there, flat line, and everywhere in between with the signal that is exactly identical, just like that. Now, what we can also do is having them in the same phase, but giving them some pitch difference, let's say like that. Now, they're not identical. One is pitched up and one is pitched down. As one is pitched up and down, as they go through oscillations, they quickly match and dismatch in phase, giving us a changeable stereo field. Just like that. So we have different things that we can do to create stereo field artificially. Meaning we can mess with the phase of one of the sound sources, so we can change the timing and change the phase of only the left or the right channel if we have an identical signal. Let's say we have a guitar recorded in mono with one mic, and we can do that. We can just delay the guitar on one of the channels and create an artificial stereo effect like that. So we can change the phase plus the pitch, and let's try this with, let's say, something different. Let's say a sawtooth like this. It's going to give us more frequency content. See that? Goes completely wild. Even detuned, just like this. Let's try that in the middle. Different view. So changing between the mono and stereo, since sometimes all of these sawtooths get into phase, but then they quickly go out. So that's about measuring stereo. We are measuring the correlation between the left and right channels and seeing how stereo they are and how mono they are, but just measuring the phase correlation between the left and the right channel. So when they're completely identical, we stay at 1. When they're completely opposite phase, they're at -1. And everything else is right there in the middle. Now, there are some things about frequencies and how our ears perceive different frequencies and how stereo they are. Under a certain point of frequencies, let's say under 300 hertz, it gets harder to determine the directionality of the sound source, meaning that any really low frequency that contains only low frequencies is really hard to determine where it's coming from. Actually, we can't determine where it's coming from. Our hearing apparatus doesn't handle those really well. That's why you've maybe seen that having a subwoofer anywhere in your studio, so the subwoofer, the speaker that produces only the low frequencies alone, If we put it to the left, to the right, it doesn't really matter. You can't really decide where those frequencies are coming from if you have your eyes closed. How we actually determine the positioning of a subwoofer is by how that phase of the subwoofer's signal is going to correlate with the phase of our normal speakers, loudspeakers. So this is what determines the positioning of the subwoofer and not the actual directionality. Shorter terms, we can't determine where low frequencies are coming from. A good thing is that usually sounds are not comprised only of low frequencies, but they do have some higher frequency content involved so that we can decide where the sound is coming from. But if it's only low, you can't